Welcome to the lecture 10 of ECE 3030. So in this lecture we will be talking about transport in MOSFETs. So we will derive an equation for the current in a MOSFET as a function of the gate voltage and the drain voltage. So what we will be discussing today is covered in section 17.2.2 in chapter 7 in the textbook by Pire. Alright, so let's get started with a schematic diagram of a MOSFET. So here we have the gate terminal and this is the drain terminal, and here we have the source. We are considering an N-type MOSFET, which means that the substrate is doped P type and L is the channel length. Alright, so now say we start applying a gate voltage. So as we have seen in the previous lecture, as we start increasing the gate voltage, the D region of the depletion width keeps on increasing, and once the gate voltage reaches threshold voltage, then we invert the channel near the oxide semiconductor interface. This red region here is the inversion region, and note that in an N-type MOSFET where the substrate is P-type, the inversion layer consists of electrons, and these electrons are mobile. Alright, so as we have said here, the threshold voltage Vt is the minimum gate voltage that is required to induce a current carrying inversion layer or required to induce the channel. Alright, and as we have seen, ideally we would want a MOSFET to have an current gate voltage characteristic that looks like this. At threshold voltage we want the current to rise very quickly, very sharply to a certain value for a given drain voltage. So we will also see how it looks, how the IDVG characteristics looks like in a real MOSFET. So this is what we want for an ideal switch, and we will see in today's lecture how the IDVG characteristics looks like for a real MOSFET. Alright. Now, important thing to note here is that so far in the previous lecture we have talked about only the direction perpendicular to the gate and semiconductor interface in the x direction. So today's lecture we will be talking about the y direction or the channel direction. Okay, so now let's see how the channel potential looks like when we apply a drain voltage Vd. Now in the source side the voltage is 0 because the source is grounded here, so the voltage or the potential in the source end is 0. On the other hand, the drain end, it is at the drain voltage Vd, so the voltage at the drain end is Vd. Now what is important to note here is that the difference between the gate voltage and the channel decreases from Vg at the source end to Vg minus Vd at the drain end. What does it mean? It means that here everywhere in this gate we have a voltage of Vg, whereas at the source end you have a voltage of 0. So the voltage across the oxide at this end is Vg minus 0, which is equal to Vg, and at this end again at the gate terminal you have a voltage of Vg, whereas the drain terminal we have a voltage of Vd. So here across this end the voltage that we have is Vg minus Vd. Alright, okay, so now let's look at how the inversion carrier density looks like as a function of the position along the channel direction or the y direction here. Alright, so now by definition threshold voltage is the amount of gate voltage or the minimum gate voltage that you need to invert the channel. Now the excess amount of gate voltage Vg over Vt goes towards creating the inversion layer. So which means that out of Vg, Vt amount goes towards creating the first creating the depletion layer and then inducing the inversion layer. So Vg minus Vt is actually the amount of voltage that contributes towards creating the inversion layer. So this is the voltage. Then if we multiply it with Cox, we get the charge density per unit area. Why is that? Because Cox, the oxide capacitance of the gate oxide, is given by epsilon naught epsilon ox divided by T ox, which is basically the gate capacitance per unit area. So if we multiply it with W here, then we get the charge per unit length along the y direction in the channel, and this charge is just the inversion charge, not the, it does not include the depletion charge. Alright, so here we have said Q, the inversion charge density at y equals to 0 at the source end, is equal to W multiplied with Cox, the gate capacitance, multiplied with Vg minus Vt. Now in this particular case where drain voltage is also 0, so we have the same amount of inversion charge density at the drain end as well. Okay, so now let's see what happens when we apply a drain voltage. So now once we have applied a drain voltage, as we have discussed earlier, that the voltage at this end is Vg and voltage at this end is Vd. So we have a voltage of Vg minus Vd that is applied, that appears across the oxide here. So out of this Vg minus Vt voltage, Vg minus Vd, Vt will go towards creating the depletion layer, the max depletion layer of the maximum width, and the amount of Vg minus Vd by which it exceeds Vt will go towards creating the inversion layer. So the inversion layer charge density per unit area will be Cox multiplied with Vg minus Vt minus Vd, and then we multiply it with the width of the transistor, then we get the charge per unit length along the y direction at the drain end. Alright, so important point to note here is that the source side, whatever drain voltage we apply, the charge in the source end remains constant all the time. It does not depend on the drain voltage. On the other hand, as we increase the drain voltage, the amount of charge that we will get at the drain end will keep on decreasing. As we increase drain voltage, the amount of charge that we will get at the drain end will decrease. So what we can do now is that calculate the average amount of charge in the channel per unit length, and that is, you can estimate it as just as an average of the charge at the source end and the drain end. So that's just a simple average, and this is also an approximation which actually works pretty well. Okay, so again the same thing over here. So the average inversion carrier charge density is half of the sum of the charge densities at the two ends, the source and the drain, and if we plug in the number, it comes out to be W multiplied with Cox multiplied with Vg minus Vt minus half of Vt. Alright, okay. So now let's do a calculation of the drain current. Now what is drain current? So if we consider just the drift current, which we'll see in one of the later lectures. So current is simply the velocity of the charge carriers multiplied with the average charge carrier. So as we have seen, this is charge per unit length along the channel direction. So we can say it's coulomb over meter and velocity is meter per second. So you get the right units, coulomb per second or amperes. Okay, so now this V is the average velocity of the inversion carriers, and what you can say is that velocity, as we have seen in the previous lectures, velocity is simply mobility multiplied with the average electric field, and mu n is the mobility of the charge carriers. Here the charge in an N MOSFET, the charge carrier is electron. So in an N MOSFET, the substrate is p type. You invert it, and what contributes to the transport is the minority carriers, which are the electrons. Alright, so here we plug in the equation that we derived for Q average in the previous slide, which is this much, and then you have mu n here, and electric field is simply the drain voltage divided by length. So length is what we call the channel length or the gate length. So it's basically the distance between the source and the drain. And if we plug in, if we now simply do this calculation, we find an equation for the drain current that looks like this ID equals to mu n Cox W by L multiplied with Vg minus Vt multiplied with Vd minus half of Vd square. All right. Now let's look back at the charge profile along the channel direction in a MOSFET. So again, starting with the case when we have no drain voltage, the charge density at the source and at the drain end are the same, but as we increase the voltage, the charge density at the drain end decreases while the source end it remains the same. Now let's consider what will happen if the drain voltage now becomes equal to Vg minus Vt. So basically you were increasing the drain voltage, and finally you get to a point the drain voltage becomes equal to Vg minus Vt. So what will happen here? So at this end you have a voltage of Vg, whereas here you have Vg minus Vt. Okay, so then what will happen is that at this end you have Vg voltage minus Vg minus Vt, so that gives you Vt. Now as we have said in the one of the earlier slides, that out of this voltage, so what is this? This is Vg minus Vt, Vg minus Vd. So the amount by which Vg minus Vd exceeds Vt goes towards creating the inversion layer. So here what we have is Vg minus Vd minus Vt actually becomes 0. So that means that when you have Vd equals to Vg minus Vt, there will actually be no inversion charge at the drain end. And this is what is called pinch off, because here when the Vd equals to Vg minus Vt, the drain end becomes pinched off. It does not have any inversion carrier. And as a result, what happens is that as you start increasing the drain voltage above Vg minus Vt, you actually do not increase the drain current in the MOSFET anymore. And that is called the saturation regime of a MOSFET operation. So what we usually do is that we write it like this, that when we have saturation, your drain voltage becomes larger than Vg minus Vd, and effectively the channel, the drain voltage or the voltage of the channel at or near the drain end effectively becomes saturated, and that voltage becomes equal to Vg minus Vt. So again, your Vd keeps on increasing above Vg minus Vt, but the effective voltage at the drain end of the channel remains constant at Vg minus Vt. So basically the amount of voltage Vd minus Vg minus Vt drops across a very small region near the drain end where there are no carriers, inversion carriers there, and as a result that voltage does not contribute towards increasing the drain current anymore, although you are increasing the drain voltage. So the way we handle the drain current equation when Vd becomes larger than Vg minus Vt is this, that at this point we replace the Vd with Vd effective, and Vd effective is Vg minus Vt, so we plug in this here, and effectively what we get is when in saturation Vd larger than Vg minus Vt, Id becomes equal to mu n Cox W by twice L Vg minus Vt square. So basically in saturation the drain current becomes independent of the drain voltage. It does not become zero, but it becomes independent of drain voltage. Even though you keep on increasing the drain voltage above Vg minus Vt, the drain current does not increase. So to summarize, these are the equations that describe a MOSFET, which we call the square law model here. When the gate voltage is smaller than the threshold voltage, there is no inversion carrier in the channel, and as a result the current is zero. It's in reality it's not zero, it's a very small number, but for the sake of this simple model we'll say that when gate voltage is smaller than threshold voltage is zero. Now the second regime of operation is when Vg minus Vt is larger than drain voltage, or the drain voltage is smaller than Vg minus Vt. We call it the linear regime of operation, and that's because here the drain current is linearly dependent on Vg minus Vt, and in this regime the current is dependent on both Vg and Vd. And finally, when drain voltage becomes larger than Vg minus Vt, then we have the current depend on Vg minus Vt, square of Vg minus Vt, and it's independent of the drain voltage. And this equation, so the current that we get in the saturation regime, we call also this current as the saturation drain current of a MOSFET, and the saturation current depends only on the gate voltage and not the drain voltage when drain voltage is larger than Vg minus Vt. Now in this equation the current is in amperes. Quite often what we do is we plot, we calculate also, we also are interested in current per unit width of the MOSFET, and here this is the equations in those cases you use. Alright,